But I won't. It's just, yeah, it's just hard. So I've got to get myself excited, you know. Ready to go for you guys. The other night, I think I was really trying. All right, well, welcome back. We have finally made some progress. Last time we started with Maxwell's wave equations. We did what we're going to do. We've done once before. What we're going to do several times again in coming weeks. We derived a wave equation. Take the curl of both sides of this Maxwell's equation and work through the mathematics. One of the exercises that I recommend you do is I took the curl of E, and you'll notice that you have the curl of H equation too. And so where I derived a wave equation for the electric field E, one of the things that you could do this weekend, if you were sort of struggling to occupy your Sunday afternoon, then you could take the curl of H and follow along and do exactly what I did before, but get a wave equation for H. And you'll notice if you do that, you'll take the curl of H, you'll have a curl of D here, and the curl of D will, through these constitutive relations, can be written as the curl of E, in which case you just pick that guy up and shove it in there, and that gives you your second derivative with respect to time. So that's exactly what we did here, right? We have the curl of H, and we substituted in Maxwell's equation. And we futzed around a little bit on the right-hand side, kept some extraneous terms, but just so you know that they could be there. And on the left-hand side, we used our vector identity for the curl of the curl, and we separated it up into two pieces. An ugly piece, a demoralizing piece, a bad piece, and something that's really nice. Something that splits apart in Cartesian coordinates and cylindrical coordinates and parabolic coordinates really, really easily. And so we did everything we could to get rid of that term. The most conventional way of doing it is just to say that you have constant charge or no charge at all. In which case, when you take the derivative of constant, you get 0. And when you do that, you get a rather nice, simple equation that you can solve. In this case, you have the gain term, you have the loss term, and you have the two pieces of the wave equation. For our fun and games, we balance these guys out, and we just cancel them out. I'll come back in and we'll do the loss case in a little bit, probably next time, just to give you a review of this. But we brought it down to our very, very simplest wave equation. Okay? Second derivative Laplacian of a vector E, balanced by the second derivative with respect to time. If you do the units, you see that this has 1 over the speed of 1 over velocity squared term. We're about to understand what that means in a second here. And I wanted to point out that this is a vector wave equation. So this is for the vector E. So this has both direction and magnitude. Okay? And what we did was we did a choice of decomposition, vector decomposition. And what we did last time was we chose the Cartesian coordinates. And the Laplacian in Cartesian coordinates breaks apart really easily. Okay? The unit vector x, the unit vector y, the unit vector z. The vector Laplacian, this is the scalar Laplacian for the ex scalar term. The scalar Laplacian for the scalar e sub y, and the scalar Laplacian for the scalar e sub z. Okay. The d by dt term also breaks apart into an x and a y and a z term as well. I don't know if I went through this as carefully as I should have, but this guy is equal to this guy. These three terms are equal to these three terms. X, y, and z are orthogonal. So this has to be equal independently from this, which has to be equal to this independently. Okay? So we set the vectors components of the x direction, the y direction, and the z direction equal to each other. And we do that because the coordinate system is orthogonal. Orthogonal is independent. Dot products go to 0 unless it's a dot product of the same thing. And so we could write a del squared E sub x is equal to mu epsilon del squared E sub y del t squared. And what I've done is I've just notated the x, y, or z as an index I. And then I gave you the warning that most textbooks get lazy about that index altogether. They leave it off, and you have this equation here, which is a scalar equation, and it looks an awful lot like the vector equation. Okay? So I'm just calling your attention to the fact that we had to do several lines of mathematics to go from there to there, and that this is really just one of 3 equations that we have to solve. Okay? Now all the equations are the same, so we're very terse in our development, but in theory, even if we solve this, we're only a third of the way there. Okay? So this is the form of the solution. We say that we're going to take our second coordinate choice, the position, to describe where the electric field is going to be in Cartesian coordinates x, y, z, and therefore this scalar Laplacian can be written very simply in terms of a d by dx squared, d by dy squared, d by dz squared. And then we want to make it simple, even simpler. Then we wrote it down for the x-coordinate. And we wanted to be even simpler, and we said, well, let's get rid of 2 of those. Let's get rid of 2 of those variations. And it turns out we have to be a little bit careful. Maxwell's equations has some rules that govern where E must be versus where H must be versus where waves will go. Not, just to be blunt about it. And so we have to be sort of careful. We cannot pick E sub x as a function of x. We have to pick it as either moving in the z direction or moving in the y direction. We have to have the electric field changing in either the z direction or the y direction, not E sub x a function of x. That's a big no-no. And what I encourage you to do, in fact, is to try that and see what havoc you wreck on, see the contradictions that come out of Maxwell's equations when you do that. Okay? It's a very, very nice exercise to do. So we picked this guy here, and I interpreted that as a plane wave. Now, I know you've all been exposed to plane waves, but I did want to emphasize again, when I say that this is not a function of x and y, what I'm saying is, if z is in that direction, then this is the xy plane, and if I scooch a little bit over here, or scooch a lot over here, or scooch way down, or scooch way up, at any instant of time in z, the voltage per meters doesn't change. Okay? If I take a step forward, it can change as I move through z, or if I stay there and hang out there and let time move, then it can change. But the fact that it's constant on this plane is the reason why we call it a plane wave. And I want to emphasize right now that's such an abstraction. It's so non-physical. Because what it means is if I go 5 miles, 10 miles, 1,000 miles, 10 light years in that direction, at that instant of time I'll still have the same 7 volts per meter. So it's obviously an incredibly gross abstraction. It's like a step function or a square wave, a square pulse. It doesn't really exist. But it may be that over a small enough aperture, it's a perfectly good approximation. Okay, or you might be able to set up a very special situation where you have over a small set of z's a plane wave. Okay, and maybe we'll talk a little bit about that as we go down the pike here. Okay. So here's my equation, And we can look at this, we can do this in a couple of different ways. One way to talk about this is we could just say, hey, I'm going to guess the solution. It's a partial differential equation. So how do you solve differential equations? You guess the solution. Here's the solution that I'm guessing. You substitute in, and because I've done this before, and you've done this before, we can make the right guess, and we show that it works. Another way to do this is, because it's a partial differential equation, we try separation of variables. And so we can see that this guess, is of the form a function that's purely of time and a function purely of z. And that's what I mean by separation of variables. And if we do that, and we substitute in, then all the time response is going to be on one side and all the z response is going to be on the other side. They're going to be set equal to a constant of integration. And we'll reduce it down to two ordinary differential equations where we can get sines and cosines or complex exponentials. Okay? So this exponential form is a form of a separation of variables, because I can write this as e to the I omega t multiplied by an e to the plus or minus I kz. Right? Okay? So just filling in a few things. The other thing I'd like to point out, and this might require a little bit of thought, a little bit more thought than what's just on the paper, but if you substitute in an e to the I omega t, or conversely you substitute in an e to the I kz, what you're really doing is you're Fourier transforming that equation. You're Fourier transforming this d by dz, or this d by dt. Do you remember a d by dt, by the rules of Fourier transforms to an I omega? D by dt and I omega are Fourier transform pairs. And so I've got two of those here, and that's the result of bringing down an I omega and then another I omega. So this exponent here ends up Fourier transforming the d by dt here. Okay? You're used to doing that in the time domain, but squint your eyes and you can do the same thing in the z domain. And so a Fourier transform in the time is this guy, a Fourier transform in the space is this guy here. Okay? So that's another way of sort of arguing what we're doing with this differential equation. Okay? Any or all of those interpretations are fine, and I think it's good to look at it in multiple ways. Okay? So I just wanted to go back over that a little bit. This is just the math part of it. Turn the crank. If I want the second derivative, I got to get the first derivative. I think the most remarkable thing about this is that there's this plus or minus in there, and that your professor did not, for once, make a mistake on the minus signs. So we got to a nice here, ending here, which is the dispersion relation. Now notice a couple of things. I did the derivatives, and I substituted back in the equation, and this is the equality that I have. One thing that I mentioned last time that I want to repeat this time here is when I divide out, or when I multiply through by e to the minus I, and I kill this term and this term, I have a left-hand side and a right-hand side that holds its equality for all space and time, for all z and t. That is what I call solving a differential equation. Is when I make a solution happen that doesn't hold some of the time, but holds all of the time. Okay, so that's just as by way of review, that's what we mean when we say we solve a differential equation, when we draw a line through those. Okay? It's linear, so it's also independent of the magnitude that we guess for the electric field. Right? So this works for 7 microvolts per meter and 7 gigavolts per meter just as well. That should give you some pause for thought as well. The remaining constants that are left over, and the reason we have just an algebraic equation is we Fourier transformed. The Fourier transform moves us from a differential equation into an algebraic equation. That's the job of the Fourier transform. is to do that for linear time invariant systems. And so we're left with this equation here. And notice what this equation here, this will be the beginning of my lecture today, is the k squared is equal to mu epsilon omega squared. Okay? Now, very simple equation, 4 characters in it, and a couple of quadratics. Nothing. The quadratics, of course, come from the second derivatives. Okay? The 4 equations. Now, 2 of these are material constants, mu and epsilon. So these are the materials. So depending on whether I'm propagating this wave, depending on whether I'm looking at the solution in free space or water or plastic or glass, I'm going to have slightly different values of a number here. Okay? The meaning of that number comes back from the wave equation, where we take a look at this product here, and we see a shift, a change, a second derivative change in z balanced by a second derivative change in t. The trivial interpretation is that this takes care of the units, but the more sophisticated interpretation is, along with the units, it's moderating the relationship between the step or the acceleration in z versus the acceleration in t, or the shift in t and the shift in z. Okay? And so, and that describes a movement, or it describes a velocity. Okay? We can get that a little bit even further. Omega is the omega of the e to the I omega t. So it depends. This is the frequency of the wave at which we're interested in. And it is the Fourier frequency of the wave that we're interested in. So we put in there 197 terahertz if we're working in a fiber optic problem, fiber optic communication problem, if in the C-band. We put in a terahertz. We put in a gigahertz if we're doing a cell phone problem. We put in 60 hertz if we're doing a power line problem. So this frequency is given to us, or we adopt that frequency based on what problem we're working on. And I made a comment about this last time, and I want to kind of emphasize it again. The frequency is what is given to us by somebody who's in charge, like the FCC. So if we're starting a radio station, we buy bandwidth from the FCC. We buy the right to operate at a frequency. And if we propagate it during a rainy day, or during a crystal clear blue skies day, or we propagate it underwater for some reason, or through the buildings, through a glass plane of a building, these change. This stays the same. K adjusts. So K is the mathematical degree of freedom that allows us to balance the equation. Okay? So this is given to us by the quantum mechanics of the problem, or it's given to us by the FCC of the problem, or the oscillator that we build, and this is responsive to that. Okay? Now, if I write this as a 1 over c squared, and I write this as a 2 pi, do you guys like nu or f for a natural frequency? F? If I write that as f, I don't want to mess with that 2 pi, so I'm going to write that as a 2 pi. So I've got a meters per second here. And I need a square here, and I need a square here, right? Square there. And so if I do my units, now I need some sort of length scale. So I could write L, but I want to be fancier than that, so I'll write a lambda. That's like an L, but it's much nicer to write, much more fun to write. Okay, since you made me do a regular letter on the right-hand side, I'm going to do a Greek letter on the left-hand side, gosh darn it. And if I cancel out the 2 pi's, I've got lambda f is equal to c. Or for some of us in the audience, lambda nu is equal to c. So this is a wavelength times a frequency is equal to the speed of light. or the speed of propagation of the signal. Okay. So what we have is we've got this plane wave, e to the I omega t plus or minus kz, and it is moving in time through z at 3 times 10 to the 8 meters per second, or a foot a nanosecond. If it goes into water, it slows down by about 2/3. Okay? A little bit less than 2/3. If it goes through glass, it slows down by 2/3. Yes, sir?
Should that be lambda square?
Yeah, that should be lambda squared. And I took the square root of both sides to get that, right? C squared. So I was a little bit. So when I take the square root, I have to be a little careful about minus signs. Okay, which is why I did an almost careful job through here. But now let's take a look at this k. Okay, and we'll go back to our solution, plus or minus k, z. And if you think through the shifts of that, the shift of the shift of a number here and a number here, the plus moves you backwards and the minus moves you forwards. Remember your rules of shifting functions around or shifting signals around? And so this plus versus this minus is whether this plane wave is coming or going. If this plane is moving towards you, positive z, it's an e to the minus kz. If it's moving away from you or positive minus z, it's an e to the positive kz, ikz. Okay? So that's where that plus or minus terminology comes from. So it was odd that I adopted it, but now we've gone back and we've given it physical meaning. Okay? And I can't go back in time, right? So I'm kind of stuck with that. But I can go backwards in space, which is kind of an interesting business. There's some, there's some things that you can get away with for if a physical system, causal, that gives you Hilbert transforms. There's certain things that go in the time domain because of that. Time only moves forward. But if z can shift back and forth, then shift invariance can go out the window. All kinds of the phase response, magnitude response can go out the window. So there's subtle issues there. Okay. Let me do one other thing for you. This is a little bit out of bounds because this is a purely classical course. But if I go h bar omega, this omega here, h is Planck's constant. If k, as in kT, moves you from a temperature to an energy, then Planck's constant h moves you from a frequency to an energy. And this is, therefore, the energy associated with a particle that's oscillating at a frequency of omega. Okay. The h bar gives me a 2 pi in the denominator. E equals h nu equals h bar omega. Well, gee, if I do that, then I should also probably multiply everything in my exponent by that. So I'd have an h bar times k. And remember that, and so that k is tagged by a plus or minus. So that tells me something about the direction that it's moving. And that's equal to the momentum. Okay? So we'll get more on that later on, but I just wanted to kind of talk to you a little bit about that. So generally speaking, this guy here is called the dispersion relationship, because if mu and epsilon are functions of a frequency, then as I vary this frequency, I change my speeds and my wavelengths and so on. Okay. Now, we really did solve Maxwell's equations. And this is a vector equation, right? So I need to remember which one I did. And I think I solved for the x component, right? So that's my solution to the equation there. And so I can substitute this equation, this guy into there. So if I take the curl of this equation here, there are 1, 2, 3, 4, 5, 6 terms in the curl, but there's only one component. So I only need to take d by dz or d by dy, but I don't have any y components, so it's just those 6 terms reduced down to one nice easy one, right? Couldn't imagine an easier curl to take. And so there's, when I take the derivative with respect to z, I pull down an ik. And this should equal minus mu del h del t. One of the things that tells me is h is equal to h sub y a sub y. It points in the y direction. That's kind of interesting. Because of this curl, my electric field points in this direction here, and my magnetic field H points in this direction here, in the y direction, perpendicular to it. Perpendicular to it, and it looks like there's an I there, which has a phase ramification. It gives you a phase shift. Okay? So when this is high, this is as it propagates. Okay? So there's some things that the math is trying to teach us here. I just want to call you. It's fun to do the math, but we have to do a little thoughtful case of this as well. And if I look at the c to the I omega t, and I'm trying to balance this back in this side of the equation with this side of the equation, well, it makes sense that I would have the same e to the I omega t plus or minus kz for the h, just to balance those two sides of the equation. And it's really not a big stretch to then come up with a guess for h sub y. So now if I substitute this guy into there, don't forget on your notes to fill in the omega t plus or minus kz there. Cancel those exponents out. The i's cancel. And I know actually what k is now, right? This k here is omega times the square root of mu epsilon. From the dispersion relationship. Take the square root of both sides, I get k is equal to square root of mu epsilon omega. So now my omegas cancel from both sides. And I can write the ratio of E naught over H naught. And that gives me the square root of, it gives me my material parameters, but written in a slightly different manner. Okay. So mu over epsilon, that's henries per meter divided by farads per meter. The per meters cancel. So this is like the square root of L over C. And the square root of L over C has units of ohms. And we call that an impedance. So you move between volts per meter and amps per meter through ohms. And so that just gives me an impedance. But it's interesting to note, right? Yes, you have a question? Okay. It's interesting to note. See, I'm hyper alert from these signals and systems. Any little twitch is going to be an objection or a question or something. So, anyway, so I have this ratio here, and I have these are material parameters. So I can ask, supposing I'm in free space, I have a mu of free space. I have an epsilon of free space, 4 pi times 10 to the minus 7 over 8.8 times 10 to the minus 12. Divide all that out, take the square root of it, and I actually get a number. And I bet most of you remember that number of 377 ohms. So there's an impedance associated with free space of 377 ohms. Now, mu, if you're propagating a plane wave, you're probably not propagating it in a block of iron, right? It's probably a dielectric. And so mu is not going to change very much from free space, if at all. Epsilon will only get bigger if you go into denser materials than vacuum. And so what that means is 377 ohms is about the highest impedance you're going to get normally in propagation. So it's really, and it's not going to be negative. It's not going to be negative. Something very strange would have to happen if it was negative. There are a few odd papers that are published now for negative epsilons or negative index of refractions or negative impedances, but truth be told, it's such a tight resonance criteria that I wouldn't worry. It can be explained better in different ways. Okay, and so you really have a very limited range of impedances to work with, 0 to 377 ohms. Okay? And I know most of you are hanging out in the RF labs and have taken other RF courses, and you're used to seeing 50 ohm lines and 75 ohm lines and things of that nature. And you won't see a 1,000 ohm line, right? Because you can only get to a 377 ohm line is what's propagating between the projector and the screen. Okay. So we have made an incredible amount of use of this mu and the epsilon. We've taken the product of it, the geometric mean of it, and we've related that to the speed. We've taken the ratio of it and taken the square root of it. We have a whole other quantity that's very, very nice, and we'll see just how useful it is when we talk about antennas and transmission lines and so on. But but that's about all we can. That's about all the ways we can rearrange those things. Now, from a more mathematical perspective, what this means is if I know the value of the electric field, I find the value of the magnetic field. In other words, if I say that the electric field is 377 volts per meter, then the magnetic field has to be 1 amp per meter. Okay? I don't have that extra degree of freedom. Which is nice because if I make a measurement of my electric field, which I can do if my wavelength is big, then I know what my magnetic field is by just scaling by the impedance. Okay. If I have E and I have h, then I can find the pointing vector. Now really what I'm doing is I'm calculating the time-averaged pointing vector, and I'm being lazy on my integral. I'm just using a little trick of complex conjugate notation. So my time dependence cancels out. And notice that I have E crossed with H. E points in the x direction, and H points in the y direction. So when you cross those together, you get A sub z. So that guy cancels with that guy by time averaging. And so we learned two things. We learned that the power flow, the average power flow, is E naught squared over twice eta. That's V squared over R, right? That's V squared over R. And it moves in the z direction. Oops, just ohms. And so we have E is perpendicular to H, is perpendicular to the flow of the energy, the flow of the power. And every time I have the that perpendicular, it's because I'm doing that cross product or the curl calculation. So if I have H, I have E. If I have E, I have D. If I have H, I have B. I've completely solved Maxwell's equations in one very special case. Now, I go back and I say, well, wait a minute. I only did a plane wave that was moving in the z direction. So I can also have a plane wave that points in the x direction and moves in the y direction. Okay? So if I have, it would be in the y direction this way, sorry. And so if I did that, then I'd have an H field that points out here. No, sorry, this direction. Then I would have, and then if I had that solution, I could add them together, and it would be moving in that direction. The z, one step in the z, one step in the y, or 45 degrees. So I can because Maxwell's equations are linear time invariant, I can find all these solutions, and I can put them together in weighted averages, in weighted superpositions. And so I've got two components in the x direction, I've got two components for the electric field in the y direction, and two components for the electric field in the z direction. So at one frequency, I've got 6 vector terms of different amplitudes. So I can be moving in any diagonal I want in this plane wave solution. Okay. I can also have a different frequency. So I can sum over frequencies. Okay. And in fact, what I can do is I can have one solution here, and then if I move over here, I'll have another solution going over here. So I can actually, by using superposition, I can actually shape my phase fronts to model a much more realistic picture. So one of the points that I'd like to get across to you is what we're doing with the plane wave solution is finding one term of a Fourier series. Okay? But you're used to Fourier series in frequencies omega, but these are also Fourier series in the direction that they propagate and the direction that they point. So it's a much, much more rich, sophisticated sum of sinusoids. Okay? And so then, so the magic of the plane wave solution is not that there are a lot of planes around, but the fact not a lot of plane waves around, but the fact that I can so easily use Fourier series to add up vectors that point in different directions, and so on and so forth. So superposition is really the key. Okay? And so what we'll do next is several different things. What we'll do over the next few different lectures is we'll do different superpositions of plane waves. And in fact, everything, a lot of what we'll do for the next month can be looked at as superposition of a plane wave going this direction plus a plane wave going this direction, or this direction and this direction. I mean, it can get, the bookkeeping can get exciting, but it's really just a very simple superposition that you've done all the time. The reason we can do superposition is Maxwell's equations are fundamentally linear time invariant, as long as the material is a simple material described by only an epsilon and a mu, a simple constant. Okay? So let me do the first example of I need a nice piece of blank paper. Let's try this. Is that okay? Can you see the bleed through too badly? No, that's okay. So what I want to do is I want to talk about polarization. Okay? I want to talk about polarization. And what I mean, and unfortunately, polarization is a word that's used two different ways in this course. That capital P, the material problem vector, that was polarization, but that's not the polarization that I mean today. I mean polarization as in what you know of as polarizers, Polaroid sunglasses, and what we really mean by that is it's the direction of the electric field. Okay? So let's talk a little bit about the fun and games we can have by adding up just two simple plane waves. Okay, things can get really kind of complicated fast with the superposition of these harmonic vectors. Okay, it's kind of so here's what we're kind of thinking about. Now, I'll start with just arguing for two charges. Okay, Q and a dq. There's a Coulomb force between each one. Q dq over 4 pi epsilon naught r squared a sub r. I think TJ talked to you for an entire period about this. I do it because I note that the force is always a vector. And therefore, if I take the limit as dq goes to 0, I have an electric field, and that electric field has to be a vector. Okay? So when I do these superpositions of plane waves, I have to superimpose vectors together. I have to consider superpositions of vectors. Okay? curl of E, curl of H equations, the wave equation, the vector wave equation. Okay, just what we did before. Adding vector components together is what we will do to describe interesting states of polarization. So it's just a superposition problem. I've rewritten my two-plane waves in a slightly different manner. So I'm looking at plane wave solutions, moving in the z direction in time. So the first one I have is one that points in the x direction and moves in the z direction. So the first term is exactly what we had before. Points in the x direction, and it moves in the z direction in time. A sub x. And instead of writing the e to the I omega t plus or minus kz, I'm being a little bit more specific. I'm moving in the z direction, and I'm also going to be definite about a phase. Okay, so instead of one of the things about the e to the I omega t notation is it allows you to be kind of a little sloppy about the phase. And one of the things that we're going to learn is the phase is how these phases come together is critical. Okay, so I'm going to work with a trigonometric expression. I'm going to work through my Euler's expression and then reduce down to this, or I'm just going to substitute, just going to solve the equations for cosine. So I've got a cosine and I've got some phase shift on it that I can wiggle around to say I want all cosine, all sine, or somewhere in between. The other wave that moves in the z direction is the wave that points, the electric field points in the y direction. So I'll have an EY prime, which is the magnitude of that plane wave, omega t minus kz, same as above, pointing in the y direction, and it has its own phase shift relative to some external clock. Okay? So this is all I mean by the superposition of two plane waves. They're both moving in the z direction, but one's pointing here and one's pointing here. Now notice, when I say what is the x direction and what is the y direction, the wave may not care. The wave probably doesn't know that I'm putting a ruler there. The wave probably doesn't care what I call x and what I call y. So one way to think about this is just any old direction of pointing, spun on an axis. And I just got my x wrong relative to what the wave thinks is x. That's one way to think about it. Seems that that's a little too simple, but that's one way to do it. Okay? All right. Now, let's just do some examples to get kind of level set on this. Sorry. So we'll go to z equals 0, and we'll set del x equal to 0, and we will set the magnitude of ex and the magnitude of ey to be exactly the same. Okay? And if I reduce down my equations, I'll have just one amplitude. The z dependence goes away, because it's just 0. I have a cosine of omega t, because I've set that phase shift equal to 0. Vector still stays in there, the a sub x. And then I have a cosine of omega t, and the y component of the electric field can be shifted in phase relative to the x component. Okay? So think about this. If they're in phase, the electric field is oscillating up and down, maximum, this way. If it's out of phase, it's doing something like this. They're orthogonal, so they're completely independent. They're not related to each other. They're orthogonal, x versus y. They're completely unrelated to each other. So this phase can be very much different from this phase. And the frequency is the same because I've made it so, but the phase is different. So a different example, a more specific example still, is the del y equal to 0. Okay? And what I've plotted here is the y-axis and the x-axis. And I'm going to clock through with respect to time. So at time t equals 1, this term is maximal, and this term is maximal. So y and x are both maximum. And so the resultant vector is there. This point here is the resultant vector of an x and a y, both maximal at that point. If I clock through omega t in time, both of those cosines start to roll down. So let's take it so they roll down to about, if they started at 1, they roll down to about a half. But this phase term and this phase term are moving exactly in the same. So both of those cosines move down to a half exactly at the same way. And that's my point number 2 here. And the resultant vector is there. Okay. If I continue down clocking through in omega t, there'll be a time when they both go to 0. And both of those cosines will happen to cross through 0 at the same time. And that's my point number 3 here. Well, the cosines continue to go south, and they both go south together, so we'll clock a little bit more so that it's the minus a half. The x is going to be minus a half, and the y is going to be minus a half, and the resultant vector is going to point off in that direction. If my cosine goes maximally negative, minus 1 on both the x and the y, then it's pointed out in this direction here. And if I come back up the cosines, I come back up the same, and the same. This line here means that the electric field is always pointing in one direction. But the magnitude has gone high to lower to 0 to negative to more negative and back and so on. It's a linear, we call that a linear polarization. And what I want to point out is if I take my little electron on a spring, a little electron on a string, I have a few of these. I take it out of my pocket, I take a piece of chewing gum and I put this electron on the end of a fishing line, and I dangle it in this field. The force at 0 pushes it this way. The force at 1 pushes it a little bit less hard in the same direction. At the instant of 3, there's no force from the electric field on that electron. And then as it goes south, the force is pulling it the other way, and so on. So if this were a wire, the electric field would be kicking the electrons on the wire. So if I have my wire this way, my field is this way, my forces on the electron on that wire is not quite as optimal. But if I turn my wire this way and line it up to that, I get a maximum acceleration of my electrons, a maximum transfer of the energy in the field into that wire. And what I've just described is something very few of you have probably ever done, but in the old days you had a television set with these rabbit ear antennas, and you'd move these rabbit ear antennas around to catch the right polarization of the signal that you were trying to watch on your grainy black and white, NTSC signal television stations. If you go to a museum, you can see that.
So putting the aluminum foil didn't help?
I keep that on my head.
No.
You never know what's out there. It's a joke. Although, so that's one example. Okay, let's walk through the same laborious, tedious argument for a delta equals minus pi over 2. And in that case, if I remember right, that guy turns into a sine, right? So I have a cosine term balanced with a sine term. So when the cosine is 1, that's at point 1, the cosine is maximal, but this term here is 0. So at point 1, the force on that little electron is always out in that direction. Okay? This cosine is going to go down, but the sine is going to go up as I clock through pi over 4, right? And so they'll be equal at that instant of time. There'll be an x component and a y component, and a resultant force on the electron that points out there. If I clock through another quarter cycle, then, or another eighth of a cycle, 2 pi over 8, then this guy is zeroed out, and this guy, the sine, is now maximum. And so y is maximum, x is 0, and I'm up here, and the force on my electron is pointing up. And as I keep arcing around, my electric field moves around in a circle. So if these amplitudes are exactly the same, and these guys are completely out of phase, 90 degrees out of phase, I'm going to get this circle. Okay? Notice that this is x, y, points up. So that looks like it's counterclockwise, right? Oh, but if I'm looking at it as a detector, it's counterclockwise. If I'm looking at it as a transmitter, it's clockwise. So trust me, people change that convention. But there is a helicity to this thing. There's a right hand and a left hand polarization, depending if that's a minus or a plus. So I have a linear polarization, and we call this circle traced out a circular polarization. Okay? Now a line and a circle are just two limiting cases of a more general curve called an ellipse. Okay? If I squash a circle, the center of the circle separates apart. I have two centers, and I have an ellipse. If I keep squashing those all the way out, all the way down, eventually I just have a straight line. So in general, if Ex is not equal to Ey, then I'll have an ellipse instead of a circle. So 9 times out of 10, or maybe even 99 times out of 100, you're going to have an elliptical polarization. But if you're working with these any state of polarization, you can always express it as the summation of two linear states of polarization, an x and a y. And that is exactly how you work with these problems. Okay? And that's why I so tediously went through the argument of this vector superposition. Because you'll be given, you might be facing a problem of a circular or an elliptical polarization, and the very first thing you do is you write it in a form that looks like that. Then you can do anything you want to this guy, you can do anything you want to that guy, and then you can see what new state of polarization you have when you're done. Okay. So if I go back to my complex notation, the electric field's the real part of some complex amplitude times an e to the I omega t minus kz. And I'll write that as I'll write A as a value AX, a value AY, pointing the X and the Y directions, and a relative phase shift on both of those. Exactly the same del X and del Y. Mercifully, I'll spare you the mathematics and probably won't even assign it for homework. But if I rearranged everything, I can write the shape of this trajectory in general as an ellipse. Okay. So EX over EY, EY over AY, and then here's my ellipticity terms. And this delta is equal to the relative phase shift. I think I have these notes on my webpage. And there's my general picture drawn. Okay. So what will happen is I'll have an eccentricity and I'll have an angle of tilt. I can rotate my axes from x and y to x prime and y prime mathematically, and I get a simpler equation for the ellipse. If A is equal to B, I have a circular polarization. If EY prime goes to 0, I have EX linear, and if EX equals to 0, I have EY. And there's the mathematics for that transformation. I'll leave it there for a little bit while you can scribble it down. But it's all. This is also on my. These notes are on my webpage, so you can pull them down later to double check it. And it is, kind of gross math. I worked it through once. Fun. But, again, it's one of those things you do on a Sunday afternoon when you've got nothing better to do while your clothes are in the dryer. You're just waiting around. So here's some examples, and again, these were developed just as in the painstaking way that I did it to start with. An EX and an EY. You assume something about the amplitudes, and you look at the different phases. We worked out this guy here and this guy here. You can see that there's between pi over 2 and 0, there's an ellipse that looks like this. So it's almost like this is opening up as I move through the phase shift. And then it's scrunching it back down. And then keep going, and you come back to there. And then, if I make some other assumption about the relative amplitudes, I still have linears, but I lose my circles. Which, if you think about it for a nanosecond, it makes sense. Because I don't have enough of the Y to fatten this circle out to its full extreme. Okay? So again, these are just painstakingly mapped out the same way I did it for you for the two special cases. It's really just superposition of two waves, two plane waves, and the 2 degrees of freedom I have are the relative amplitudes and the one relative phase. Some rules, I guess, if you want to memorize. I don't. But linearly polarized light is integer values of pi, the phase shift. Circularly polarized light, you have to have the magnitudes equal the same of the two waves, and you have to have a plus or minus pi. Or maybe that should be plus or minus pi over 2 on that. And the ellipticity of the ellipse is the b over the a of that formula. Okay. Now, what's kind of interesting is it's pretty obvious, I think, that this guy is, and this guy are two basis sets. You write one as an x, one as a y, or an x prime and a y prime, and that's a decomposition, a vector decomposition. So if you have any state of polarization here, I can break it up into an x and a y component. So any state of polarization can be written as two linear states of polarization. But what's also interesting is you could do the same thing with two circular states of polarization. So some people like to take any ellipse and break it up into a circle minus another circle. Two circular states of polarization is also a basis set. Okay? I think when they do that, they're just showing off. Okay, but some people will swear that it's the easiest way to do the problem. There's sort of a standard procedure for solving polarization problems. And typically what you have is you've got some sort of prism or crystal or birefringent element, something that has a broken symmetry in the x and the y. Remember the materials lecture? And so you have a state of polarization in, and you have a state of polarization out. You take the state of polarization in, you break it up into its two components, two orthogonal components. You propagate it through the crystal, and you do two things. You measure the amplitude change of each of those states, what's happening to EX versus EY, and you take into account the travel time, which is the phase. And I've written this in terms of the length of the crystal, the speed of light, the frequency that you're at. This can be rewritten as the wavelength. But remember, I like to work in frequencies. And I've written this in terms of the index of refraction difference between the x and the y components. So there'll be a phase change. So what will happen is the relative amount of EX and EY will change, and the relative delta of the phase will change. And so the state of the polarization here will necessarily change with the state of the polarization out there. But this is the way to solve a polarization problem. So if you get all confused about ellipses and stuff like that, don't. See them for what they are, a superposition of two plane waves. They're orthogonal, so the crystal is going to act on one in one way, on the other in another way, and you're going to be left with a new state of polarization. Think about your Polaroid sunglasses. The attenuation is everything in one plane and nothing in the other plane. Phase doesn't even matter on that problem. Okay? So that's one way to change the state of polarization with just the amplitude change. Much more elegant to do the phase change, because then you don't throw out any energy. I'll just point this out to you guys. There was a set of papers that was written in the 50s and early 60s by a guy named Jones, and he came up with a calculus for describing all this stuff. And really all he does is he stacks up the x component as one vector and the y component as the other vector. And so this is now a vector, and he's able to describe different states of polarization in terms of different vectors. And again, you're just plugging in different AXs and different deltas. But it's kind of nice because now your elements can be written as 2x2 matrices and cascaded together. And so a lot of these 2x2 transfer functions can be done here. He wrote a series of about 7 papers, fairly thick papers, a dozen pages each, describing this in great detail. And it really is a very useful way of analyzing. If you have to do a lot of these polarization problems, these are great. Anybody guess where Jones worked? '50s, '60s? No? Good guess, but no. You're on the right track. A company called Polaroid. You may have heard of the cameras and stuff like that. So he was stuck doing all these polarizing systems. He came up with a way of easily calculating these. Okay? So Jones vectors, I just point you to that. So really, I offer that more as just a non-trivial example of the superposition problems that we do when we have multiple plane waves. You not only have to worry about amplitudes of your vectors, but because they're harmonics, you have to worry about how they add up in and out of phase. Okay? And it's just a little bit more bookkeeping. But remember, that's only 2 components out of a possible 6 over different frequencies, and so on and so forth. Okay?